our calc project, William and I decided to make a potato gun. We wanted to figure out the optimal angle of launch to get the farthest away from our original launch position. We knew that to begin, we had to break the concept down to the basics and separate the object's travel into its x and y components. The acceleration of the y component we knew to be just negative gravity, and to find the velocity we would have to take the integral of that acceleration. The c in the velocity would represent the initial velocity. Next, to find the position graph, we would have to take the integral of the velocity. The c in the position would represent the initial position. Next, we knew that the acceleration of the x component was 0 because we were assuming no air resistance. The integral of the acceleration would again give us the velocity function, and the c in the velocity equation would represent the initial velocity. Taking the integral again would give us the position with c representing the initial position. We now have created our baseline of kinematic equations. From here, we want to look at the x and y components of the launch. We know there's an initial velocity at the theta angle, but we want to separate that initial velocity into its x and y velocities. Using trigonometry, we can see that the y initial velocity would be velocity initial times sine theta, and the x initial velocity would be velocity initial cos theta. We know that when the y position of the object is equal to 0, the maximum distance has been traveled by the object. From this point, we can take our original y position equation and set it to 0. We know that the initial y position is 0, so we can cancel out that part of the equation. We can also plug in the y initial velocity from our trigonometry calculations earlier. From this, we can solve for what time it will take for the object to reach the end of its path. We got velocity initial times 2 sine theta all over gravity for the time it will take. So now that we know the time it will take for the object to land, we can now plug this time into the x position equation and solve for the x position. Again, we know that the x initial position is 0, so we can cancel that part out. We can also plug in the x initial velocity from the trig we did and solve for the position. This gave us velocity initial squared times 2 cos theta sine theta all over gravity. Something special happens here, and where we can see a trig identity. 2 cos theta sine theta is equal to sine 2 theta, so we can now plug that in and get velocity initial squared times sine 2 theta all over g. We're almost there. We're looking at velocity initial squared sine 2 theta over g. The only part that we are trying to solve for is when sine 2 theta is the highest it can possibly be. Sine has a maximum of 1, so we would set sine 2 theta equal to 1 and solve for theta. Here we can see that theta would have to be 45 degrees. After this, we went outside to test our theory on the football field to see if it was really true. This is the potato gun we built to test this. We started off with a 45-degree angle shot with 20 psi of pressure, and the results were phenomenal. Next, we tried a 20-degree angle with 20 psi, and it was rather lackluster, but it was also what we expected. Finally, we did an angle slightly above 45 degrees at 50 degrees, and it came very close to 45, but still fell short as we expected.